Today, I'll be talking about how design of two-dimensional silicon nanowire arrays improves anti-reflection and light trapping in silicon solar cells. Go over the introduction, methods, anti-reflection, absorption of the substrate, light trapping, and conclusion. So, due to energy crisis and the usage of fossil fuels, renewable energy is getting really popular. Among all the different types of sources, solar power has been really popular. And silicon solar cell is one of the most common solar power. On the other hand, our technology has been improving. Wafer thickness has been reduced, and it is expected to be down to 120 nanometers by 2020 for the cost concern and for improved efficiency. However, there's one problem for solar cell. The substrate will reduce to the absorption depth of the incident light, which also means that there will be significant losses because originally the solar cell, the efficiency is not high to begin with. So what should we do? We should improve the light management of the solar cell, including anti-reflection, scattering, and light trapping. Silicon nanowire array can totally do that. It has efficient anti-reflection, structure, and good light trapping abilities. Now go over the method. First, in the paper, it is assumed that silicon nitride can be uniformly deposited onto silicon nanowire array, and the geometric factors are given below, such as S for the thickness of substrate, the height, the width, and the thickness. Throughout the report, rigorous coupled wave analysis (RCWA) was used to investigate optical properties of silicon nitride-coated silicon nanowire array. And RCWA is a semi-analytical method in computational electromagnetics that is most typically applied to solve scattering from periodic dielectric structures. The overall anti-reflection ability is evaluated by the average reflectance under a certain incident spectrum, and the equation is given on the bottom right. The 5 lambda is the incident spectrum, and then we use air mass 1.5. R is surface reflectance, and it may change due to wavelength. The minimized R bar can be obtained by changing the geometric factors H, W, and T of the anti-reflection structure. Besides evaluating the formula, the RCWA method is also used to evaluate the anti-reflection. And RCWA is also used to evaluate absorption. As for light trapping, semi-quantitative analysis is used. Basically, it is tracking the light path and then calculate the internal reflectance at each surface. Now we go over anti-reflection. Reflectance in major response region of the solar cell are from 300 nanometers to 1100 nanometers. And air mass 1.5 spectrum is used because during the daytime throughout the day, the air mass can be higher and lower. And 1.5 is the best average, and it's most commonly used to doing such evaluations. There are two graphs, A and B. A is a graph of bare silicon nanowire array, and B is silicon nitride coated with silicon nanowire array. As you can see from graph A, the reflectance is relatively high. Before 600 nanometers, it's really high, and as the wavelengths increase, it goes down a little bit, but still it's quite high. As you can see from graph B, that silicon nitride coated silicon nanowire array actually improves the reflectance by a lot, well, reduces by a lot, as you can see from the color of red, green, and blue lines. And the black line is just bare silicon nanowire array for you to compare as a reference. As you can see, the optimized reflectance around 600 nanometers. Then when you coated silicon nitride with silicon nanowire array, it can go as low as 1.62% at 600 nanometers. There are also two graphs, C and D. D shows the average reflectance. D is the thickness of silicon nitride and versus the height of the silicon nanowire array. At the right, the different coloring, that's the percentage of reflectance. So from graph D, one can tell that the average reflectance is very sensitive to the thickness of silicon nitride. And then from graph C is the width of the silicon nanowire array versus the height of the silicon nanowire array. And then from graph D, we realize that the optimized for the thickness is at 6 nanometer. For the graph C, we'll fix it at that. And it shows that graph C shows that the width and the height of silicon nanowire arrays can change in a large value range to still reach 2% of the average reflectance, which is the blue region. What does that mean? It means that it has good deviation tolerance, which is good for fabrication since it got so much tolerance and so much room to work with.